Okay, so I'm quickly going to go over this just for sake of the screencast. Write down, please. So we had water dripping through a coffee maker. The amount of coffee in the cup is given by a differentiable function c, where t is measured in minutes. Selected values of c of t, which is the amount of coffee in the cup, measured in ounces, is given in the table. Use the data to approximate c prime of 3.5. So you find where 3.5 would go. Whoa, stop. So like right here, so you go up one, down one from that spot, and you do slope. All right, so 12.8 minus 11.2 over 4 minus 3, and then so your answer is 1.6, and then the units would be the units of C over the units of T, ounces per minute. Change in Y, change in X, and there you go. Just for purposes of the video real quick, I asked students to explain the meaning of what this means, and here's your explanation very quickly. So when 3.5 minutes have passed, so that's your input, always start with your input, then state what the function represents. The function represents the amount of coffee in the cup. And then you do this next part is the same for all of them. Is changing at a rate of. Is changing at a rate of 1.6 ounces per minute. So that, if you're asked to explain the meaning, that would be your explanation. All right, this is section 2.8, general derivatives, last section of the unit. And we're going to start with this guy right here. So yesterday we did a problem towards the end where instead of plugging in a number for A, we kept AA. So I don't know, do you remember that? So we did one limit where we kept AA, and then what I was saying at the end was, hey, if we keep AA, then at the end, if you need slopes at a bunch of different x values, you can just plug them in for A at the end and not have to redo the limit over and over and over and over. That's called a general derivative, and that's actually what this formula is here. So all right, so this f prime of x, just notice this formula, this is the one that we've been using. This formula is the exact same thing. It's just that A typically represents a constant and X typically represents a variable where you can plug stuff in. So instead of calling it A, we call it X. So, but it's the exact same formula, just changing the A to an X. So when you have this formula, this A is typically a number. Here, we keep the A as an X, and then it just stays X throughout the whole derivative, through the whole limit. And then in the end, your answer will actually have an X in it, and then you can plug numbers in for X and get the slope at any point. That's called the general derivative. Now, personally, I like to call it the slope finding function. So your general derivative is a slope function. So if you have some regular function, your inputs are x's, and your output is some point on the graph of that function. When you have your derivative function, your input is still x, but your output is the slope of the graph at that point. It's not a point on the graph, it's the slope of the graph. Do you understand the difference? So an f of x, if you have a graph of f of x, then you plug in an x, you get out the y on that, which is a dot on that graph, right? If you have an f prime, you plug in the x, and then your answer is the slope of the graph at that point. Okay, all right. So we're going to do one. We're going to do like probably the easiest one we could do. So if f of x equals x squared, we're going to find the general derivative. Then we're going to find the derivative at x equals -5 and write the equation of the tangent line. So general derivative, has anyone in here had calculus before? Nobody? Really? Okay, so I'm just curious, because in first period, I had 4 people in class who knew the derivative of this before they started. Anyone know the derivative of x squared? No? Good, okay, wonderful. We're all in the same boat then. All right, so, yeah, right. What is it? Okay, this is a good try. Okay, so, all right. So what I want you to do, don't keep going, but first step is just see if you can write the setup with your limit. See if you can write your limit to set this up and then stop. Because I want to kind of gauge us to see where we're at and make sure we all do the same limit correctly before we move forward. Do you want me to write the formula? Here, I'll write the formula just in case you need it. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. That's your formula. H. Well, we're about to move on, but thank you. Okay. So for this problem, let's check our setup. F of x plus h. Is that x squared plus h?
No, it's x plus h squared.
Ah, okay. Thank you. It's x plus h quantity squared. So x plus h squared minus, what's f of x? X squared over h. All right. Okay, now keep going, see if you can find this limit. Oops. All right, so foiling this out, we get x squared plus 2xh plus h squared minus x squared. And then you can cancel your x squared terms. So we get 2xh plus h squared over h. You can cancel an h from every term. And you're left with 2x plus h. So does that mean my derivative is 2x plus h?
No.
What, Keegan, what do I have to do?
You have to plug in 0 for h.
Oh my God, 0 for h. Okay, so then I plug in a 0 for h, and my final answer is 2x. So, all right, let me see. I gotta learn these names. I'm close. I actually think I know your names, but I don't want to say the wrong name by accident because then I would feel really bad. So, let's see. Alec. Hi, Alec. What does this 2x represent? What does it give us? Oh my goodness, that was really well worded. Like that was better than I was expecting. So well done. Okay, so this gives us the slope of f of x at any specific x value. And it's by slope, we don't mean an average rate of change, we mean an instantaneous rate of change, right? This is the instantaneous, you plug in 1x, you get out your slope, right? Instantaneous rate of change. So if I want the slope at -5, right? So f prime of -5 is another way of saying the slope of f when x is -5, right? Okay, so if I want this, I can just plug it into my new slope finding function, and I've got it. Does that make sense? So this number right here, this f prime value, that's a slope. Gavin, what 2 things do we need to write an equation of a line?
We need our point and slope.
Point and slope. We have the slope. The slope was -10. Do we have a point?
Yeah, plug in the -5.
Into where?
So the f of x is x squared.
Good. Whenever you need a point on a function, you got to use the original function. Because the derivative isn't giving you a point, it's giving you a slope, right? So if I want the point, that's f of -5. That hasn't changed. You've been doing this for years, right? So if I want a point on the graph, I plug into the original function. So this is -5 squared because it was f of x equals x squared. So I've got 25 as my y value. So my point is -5, 25. Yes, all right.
Do we need to have the 2x up top? We need to have that because I initially plugged in -5 into x and solved an x.
Okay, so you did what's called a derivative at that point instead of a general derivative. And the whole point of today, you did what we've been doing, which is awesome. So you've been practicing what we've been doing, which is finding a derivative at that one spot. But the whole point today is to learn how to find a general derivative, which means don't plug in the number right away. Keep x, get that general derivative, and then plug in the number at the end. Okay? We do that for a couple reasons. One, because that's how, like, once we start chapter 3, like on Tuesday, right? So 1 week from today, we're going to start chapter 3, which is all about derivatives. 100% all derivatives we will find going forward will be general. So we need to move to general. So that's what we're doing today, is kind of bridging into general derivatives. All right. So good question. Okay, Ari, I'm going to stick with you. So we have a point, we have a slope. Can you tell me how to write an equation for this line?
Y minus 25 equals -10x plus 5.
Times x plus 5. That is gorgeous. I love it. That gets a smiley face. Everyone comfortable with that? Now in WebAssign, I've been noticing that when they have you write an equation, that it's solved like y equals. So I apologize that for WebAssign, you're going to have to do a little manipulating. I think, don't get mad if it's not true, but I'm pretty sure in WebAssign, if you just kept this and just put a plus 25 here, that they take it. Yeah. So you don't have to sit there and distribute out and combine terms. You can just keep this like this and put a plus 25, and then you've got it, right? Okay. But anyway, on your test though, point slope form is fantastic. Okay, good. Any questions on that one? So the next example, I'm going to change and do Getting to Know You Tuesday. Okay, so Keegan, you're going to be the official number picker. Pick a number between 1 and 32. Oops, no. So this problem's from 1986. It was on the BC exam, but it's absolutely something you guys could do. For all real numbers x and y, let f be a function such that f of x plus y equals f of x plus f of y plus 2xy. And such that the limit as h approaches 0 of f of h over h equals 7. Part B, which is the only part you have to do, use the definition of the derivative. That's the definition you guys just learned. Limit as h approaches 0 of f of x plus h minus f of x over h. Use the definition of the derivative to find f prime of x. So take a minute, chew on it. You can think quietly. You can discuss with your group members. After a minute, I'm going to give you a little nudge. Prime, come on. So f prime of x, we know, is the limit as h approaches 0 of f of x plus h minus f of x over h. Now I'm going to get away from this for a moment. Let's look at this f of x plus y. X and y are variables. So like say I wanted, based on this, if I wanted f of 2 plus 3, that would be f of 2 plus f of 3 plus 2 times 2 times 3, right? You can plug in whatever you want for x and y. They're variables, right? So this is f of x plus y. I need f of x plus h. Could I plug in an h for the y here and replace this with h's plugged in for the y's? Is that okay?
Oh, yeah.
Try it and see what happens.
That is alright.
Oh, good.
I'm so Wait.
Yeah, it does.
Don't think ahead, just do it.
Just do it.
Just do it. Sometimes it's better to write than to think.
Yeah.
What is it? Oh, it's minus f of x. Okay, you can't.
Then you
Wait, why is there a y? You have f of y plus 2x.
Oh.
Because f of h would
So
be.
is that just the
I think
answer?
f of h right over there. And then you got f of x plus h. That. F of x.
Wait, how'd you get rid of the y? Oh, you figured it out.
It's pretty obvious.
There's y and an h. Y and an h. Yeah, f of y is 2x plus h, right? Wait,
I figured it out. Oh, and then you cancel these. Like, oh my god, this is. Oh my god. Math is this math thing. What the heck? It's not fair. Wait a minute. Wait a second.
Wait, so that's f of 0.
I've been
did you
there.
like factor out the y?
Yeah, I'm also trying to.
How do you take it? H out of
Oh, no, because
Did you get to this part?
you cancel out the f of x, right? So then you get this, so f of h plus 1h over h.
Yes.
I know, right? So you That's this is the same thing as this. So you know f of h over h is 7. I know that we use it. So you're getting the limit of it.
And you factor out the y, so it's f of
You get
1
the plus.
I'm so
Okay, if I'm wrong, you don't have to, because this is still in.
Wait, do we take it? It's better not be a question.
Oh, and then you have 7 plus 2x.
Alright, I did not pause the recording, so I'm gonna go up and continue this. Cause this is really not, it's not that important, but it's kind of fun. Alright, so f of x plus h, based on this definition, is f of x plus f of h plus 2 times x times h. This is my f of x plus h. Then I have to do minus f of x over h, right? This is this. How did I get it? Well, if f of x plus y, right, these are any inputs we want. So, like if I want f of x plus h, I'm just replacing my y's with h's. It's changing the letter. I could do the same thing if it was f of x plus 5 and change the y's to 5's, right? Okay. So I've got that. Now, the limit's not so scary, right? So now, the f of x's are gone. And we get this. This is testing to see if you know your properties of limits. Because we are given the limit of f of h over h, but we're not given the limit of f of h plus 2xh over h. What do we have to do? We have to split it. Very good. I love those words. So the limit of the sum is the sum of the limits. This is this. No, I did before. What's that? Right? You just split it up. Just common denominator, right? Yes. So you just split it up. What is this guy? Do you guys, I don't know if you wrote it down at the beginning of the problem. It's 7, right? This guy, what can we do? Cancel the h. And what's that limit? What's the limit as h approaches 0 of 2x? 2x. What's our derivative? 2x plus 7, or 7 plus 2x. Kind of fun, right? It's not that bad. See, it's the hard part with most calculus, especially when you get into some of these funky free response problems, the doing isn't the hard part. It's the knowing how to start. That's the hard part, right? And that's the part that you guys need to make sure you're practicing. So like when you're doing your homework, if you ever have a problem and you don't know how to start, that's the part that you need to be like really working on and forcing your brain to like grunt through. Well, I don't know how to start. Let's try this. Let's try this. Oh, that didn't work. Let's try this. Don't ever just say, I don't get it, leave it blank and move on, right? We always grunt through because the more you train your brain to attack, the easier they'll become, right? Your brain will start getting used to it and it won't feel so scary anymore. You'll just like, oh, I see a problem. I don't know how to do it. That's all right. Let's attack, right? Okay. All right. I don't mean to bring, okay. I was scolded over the summer for bringing violence into the classroom by saying words like attack, right? So I don't mean to do that. I also used to have a really bad habit. Whenever I would say I was canceling, I would never say cancel. I'd always say let's kill off the H's. And again, like so I apologize. I don't mean to like use like violent metaphors. So anyway, but I do want you to like take these problems head on without fear. Yes. I would be happy to go up for you, Charlie. So there's our.
I mean, if you think about it.
Oh, see, now does it make sense? Yeah, that this part. Yeah, that was the important part. All right. Vishal, are you good?
Yeah.
Okay. You sure? Yeah. All right. This one we're going to do on our whiteboards. This is kind of fun. So you know what? Before we do this, let's make sure we get something written down. I got to make sure this is in your notes, okay? Don't let this start. It's not scary. Don't let it scare you. All right. I'm not even going to let you see it, okay? All right. So we're going to talk notation. Notation. So you have learned the notation for a derivative is f prime of x, right? So I'm going to do an example. Suppose f of x equals x squared. You now know f prime of x is 2x, right? We call this the derivative of f. Is that okay? Yeah. Okay, I saw some angst. Okay. All right. Suppose we don't call it f of x. Suppose we call this function y. Then how do we write the derivative? Y prime. So f prime and y prime, they're the same thing. They both mean derivative. It's just that one's in function notation, one's not. Yes.
On the test, will we have to derive to find the general derivative of x squared, or can we just know it?
On the test, I would never ask you for just the general derivative of x squared.
Okay, but like if we need to apply it to a problem, can we just like know that?
No, I'm gonna want to see the work. But I can promise you, like you have my word of honor, there is not a problem on your test that says what is the derivative of x squared. Okay. All right. So, does everyone understand? Like you can use f prime, you can use y prime, they're the same thing, right? Okay. Now, these two types of notation these are based on Isaac Newton's work. There was a separate mathematician who also was working on calculus at the same time as Isaac Newton. His name was Leibniz, and Gottfried Leibniz. And he introduced a different kind of a notation. So he said, hey, derivative gives a slope, right? So don't write this down yet, but like looking at your old-fashioned slope, so change in y over change in x, he thought to himself, well, what if we use notation where we're kind of representing this, but instead of this delta, which means change, we don't have any change anymore. So he came up with saying, so now our derivative, let's call it dy dx, and this d is going to kind of represent the limit as the change approaches 0. So like dy dx is another word for derivative. And it's kind of, it comes from this definition of slope, change in y over change in x, except the d is really like when your change approaches 0, when there is no change, right? So we're kind of gone from delta y delta x to dy dx. So that's now Leibniz notation for derivative. All of these things mean the same thing. They mean derivative, right? Okay, so for example, for this one, I could also write dy dx as 2x. It's synonymous. Same thing, same thing, same thing. There's more. So you can also, if you think of this as like a fraction, which it really is, so we won't treat it, we won't tear it apart for a while. We will eventually tear this thing apart and treat it as a fraction. But right now you think it's just one thing. But if it really was a fraction, this is really thinking it's d of y and d of x, the derivative of y, the derivative of x, but it's that d of, but if you kind of think of it like multiplication, then you could put that y in front and have the same thing. Now, what I like about this guy right here, this is really kind of like a noun, like dy dx is x squared, or 2x, or whatever we're doing, right? This guy, this d dx, that's more like a verb. It's saying, find the derivative of whatever is next to me. So this kind of means find the derivative of, and then this is what you're finding the derivative of. So when you see d dx and something sitting next to it, again, that just means derivative. Now, the nice thing about this is the y doesn't have to be a y. You can actually put the actual function right there. So this means derivative of x squared because y is x squared. This means derivative of x squared if you have the function and it hasn't been named. Either way, when you see d dx, it means find the derivative of whatever's next to it. Yes?
So say they give you our x value, would you put the x value right there?
Okay, that's a good question. So how do you indicate when you're plugging in when you don't have function notation, right? So the same thing goes like in the past. Like when you were in Algebra 2 and you had an equation y equals 3x plus 5, how did you write what that was when x was 2? All right, I'll show you. You guys don't know, but you should, but no one ever teaches this. Okay, so proper notation for plugging a number in, again, that's bad words, for substituting a value for x. Does everyone have this? Like, does this make sense? So suppose let's just stick with the same function. So we know f prime of -5 is -10, right? We just did that. Okay, so suppose I want to write it, but I want to write it in without the f's, right? So I'm writing it with y's. So in math, first of all, you will see a lot of people take this liberty, even though it's technically not correct, but even like professors, you'll see people go ahead and just kind of write the y as a function. That's okay, I don't really care. However, correct notation, say I have this, right? And I want this at -5. How do I do it? I'm not going to put it all of -5 here. So whenever you're in math, you have this vertical bar. That means evaluate. And then you write a little lower thing that says evaluate at x equals -5. So whenever in math, if you ever see something written and it's got this vertical bar with an x equals -5, all that means is substitute -5 in for x. Oh, whoops, yeah, because it's derivative. So the derivative of x squared at x equals -5 is. So the vertical bar notation is correct. How many of you own a TI-89 graphing calculator? 2? Just 2? Only 2 in the whole room? Just 2? Okay. So you too, just so you know, whenever you're typing functions on your main screen, if you need to plug in an x, there's a vertical bar on your calculator, and you just hit it, and then type x equals -5, and it'll plug it in for you, right? So, and the nice thing about the 89 is it'll bring that same line down, so if you have to plug in a bunch, you just change the number to whatever. Just keep doing it. But vertical bar means evaluate at. Okay, one last thing to write. Actually, a bunch of last things to write. So, wording. So, noun, derivative. The verb for derivative is not derive. That's a big pet peeve of mine. I don't have many. That's one of them. So we don't, when we derive something, it means we create it from scratch. Like we could derive the formula for a derivative, right? It means we came up with it. We figured it out. We derived it. But when you're finding a derivative, the verb is differentiate. Differentiate. So the verb for derivative is not derive, it's differentiate. Guys, I know the bell rang. If you have 10 seconds and can stay, your homework tonight is going to ask you about functions being differentiable. If you don't have time to write it, these will be in the Smartboard notes. There are 3 conditions for a function to have a derivative. It's got to be continuous, it can't have a vertical tangent, and it can't have a sharp turn. Those 3 conditions have to be met for a function to have a derivative. So if you want to write these down, that's great. If you don't have time, that's okay. I'll put them on the Smartboard notes, and you can look them up later on. Okay, that's it. That was the last slide. So have a great day, and I will see you tomorrow.
Thank you.
Tomorrow we start reviewing for your test. Tomorrow we'll talk about your test.